Hello. In this practical class, we will be talking about the ultrasonic welding process. So, the main objective of this practical is to talk about the working principle of the ultrasonic welding, give the demonstration of the ultrasonic welding for joining of the polymers, and then also to morphology or study the effect of ultrasonic welding parameters on the joint characteristics, say the joint interface morphology or the microstructure and mechanical properties, and then analyze the results on the joint characteristics, finally to see the conclusions based on this study. So here if we see the working principle, this process basically depends on the frictional heat generated at the interface, and this interfacial frictional heat generation is realized by providing the high frequency low amplitude mechanical vibrations. So if we see a lot of interfacial frictional heating happens here, that leads to the different kind of the effects, which may be in form of say melting or just the thermal softening of the metal at the interface. So depending upon the workpiece materials, melting is frequently observed in case of the polymeric materials, while it may not be the target in case of the metallic material. However, accidentally or abnormal welding conditions may lead to the localized melting here and there. So what we do, the components to be joined, say component 1 and component another, if these are to be joined, then these components are placed in the lap joint configuration, and then with the help of the tool being used in ultrasonic welding, that is called sonotrode or horn also. So the vibrations, mechanical vibrations, are applied to the workpieces through this horn or the sonotrode, and this will be facilitating the two things. One is the application of the compressive load or the clamping pressure, you can say, at the same time the mechanical vibrations. So these mechanical vibrations mostly act laterally in the plane parallel to the joint interface. So the combination of the compressive load, the shearing kind of the movement through the application of these mechanical vibrations, this combination of these two things leads to the lot of interfacial heat generation due to the friction, and that is what we can see here in this another diagram. If we check this, so this is the sonotrode. So in order to provide very intense and focused vibrations, the sonotrode tip is not made flat, but it is given some different kind of the features at the surface which will be coming in contact with the workpiece. Okay, and this kind of the geometry we can use from the top and the bottom side. It helps in focusing the application of the vibrations, so that the enough interfacial the softening or the melting can be realized through the interfacial frictional heating. Okay, so these are the typical the sonotrode tip surface morphologies. Say just for an example, it has been shown here, and when the sufficient on the application of the vibrations, when sufficient heat is generated at the interface, you may get the localized melting near the surface layers or a significant thermal softening. So the combination of the normal load coupled with the shearing movement, this leads to the, let's say, the surface of one side is getting softened. Similarly, the surface of another side is also getting softened, and these are experiencing the shearing movement. So softening, or sometimes coupled with the localized melting, will be leading to the intermixing of the metal from one side to another. Okay, so this in turn will be leading to the, like the metal from one side is getting mixed with the metal of the another side, like this. So that is what we will see more clearly in the next diagram here. So what we see, whenever the sonotrode is brought in contact with the surface of the workpiece, so here, like say, the horn or sonotrode surface touching to the surface of the workpiece. Okay, so we apply the clamping force or normal force as per, and then we give the vibrations. So when these vibrations are given, there will be interfacial movement. So say one part is fixed and another is being moved under the normal load. So this will be leading to the rubbing at the interface. So this rubbing will be leading to the, like say, the removal of the breaking or damage or the fracture of the surface impurities, oxide layers. So in turn it will be facilitating the surface cleaning. So that is one thing that will be happening, and with the continued the relative motion at the interface under the normal load will be leading to the increased frictional heating, and increased frictional heating will be leading to the thermal softening, and that in turn will be leading to the increased interfacial surface layer deformation. They will be coming in close contact with each other, and so the metal to metal contact between the two components at the interface will be increasing. So you can see that the metallic intimacy zone will be growing gradually, and eventually we get the metallic intimacy between the two components. So this in this process we get the variety of situations. As I said, there may be complete melting like in the polymeric materials, or there may be significant rise in temperature, maybe 0.4 to say 0.6 times of their melting point, so which many times is high enough to facilitate the recrystallization, to cause the heat affected zone or the development of the heat affected zone formation, recovery and recrystallization, even over tempering, over aging. So those things will also be affecting the mechanical properties depending upon the condition or the type of the metal. Okay, so initially the sonotrode tip will be coming in contact in the phase 1, the pressure is getting increased, then that pressure is maintained. Okay, and once so initially pressure is increased, then vibration starts. During that period heat generated will be leading to the melting. So this is a typical cycle or a stages for the polymeric material, where the melting is taking place, then the two are getting completely coming in contact with, then the steady state metal flow, and then eventually hold, and the cooling stage, that's the fourth stage. So this is the typical kind of the stages that we get in case of the polymeric material. Our agenda may not be to melt the material at the interfaces in case of the metallic joining using the ultrasonic welding. So this is another one schematic to explain that how the ultrasonic welding works. In here, if we see the two components to be joined are under pressure from the horn, and this will be applying the load under the mechanical vibrations. So the melting, both the sides take place, and due to the relative motion, intermixing of the metal from the two sides will be taking place, and eventually on holding and cooling, after the cooling, complete the joint is formed in case of the polymeric material. So the pressure is applied, and then horn generates the vibrations, and then the frictional heat will be facilitating the melting in case of, and then it will be generating heat enough to cause the thermal softening, melting, and development of the weld joint. Okay, so these are the, like say, the four different stages in case of the polymeric material, where we can see the melting starts in stage 1, then coupling, then steady state flow, and the holding, the cooling stage. Okay, so the pressure up to third stage is maintained, and thereafter it is reduced in the cooling stage. So this is what we can see ultrasonic welding in case when the metal to metal joint is developed. So when metal to metal joint is being developed, say the two different types of the aluminum alloy, aluminum copper alloy, aluminum magnesium silicon alloys. So when this kind of the so that's what we can see, the clamping force and the vibrations being applied, that will be these will be applied through the sonotode onto the joint interface between the component to be joined. Okay, and what will be the joint morphology, what will the extent of heat generation, what will be the maximum temperature rise, whether there will be melting or no melting, just thermal softening, all that depend on the amount of energy being supplied. Okay, so say the power of the ultrasonic machining system is say 2400 watt, and the kind of energy being applied for development of the joint is 950 joule, and the pressure of the 482 kPa. So this is the kind of the joint morphology we get it at the high magnification. We see like this is mostly the flat joint interface morphology with a little bit intermixing between the two metals. If we take the example of the metal and polymer joining, so metal by and large remains stable, but polymer being of the low melting point, say polymeric material gets melted in process of the joining, and this is what we see here, that the completely the joint at the metal and aluminum sheet and the polymeric material composite material is being developed. Okay, so this is just an example to demonstrate what happens when the amount of energy being supplied to develop the joint between the two different metals. Say in this case the steel is being joined with the aluminum alloy. So what we do, we take the two components like this, okay, and we apply the sonotode. Sonotode having the like a very typical geometry at the surface through which these are applied, so that you can apply very intense vibration in localized manner wherever you want to develop a joint. These are now, these will be increasing the localized pressure at the surface of the workpiece, both the sides. Okay, so because of this we get indentation also in these surfaces of the workpieces, and these indentation, you will see the surface of the workpiece will show you a structure like this. Okay, like this. So this will be causing the thinning of sheet, and here you may have the joint interface like this. So thinning of the sheets at the location of the joint is one of the aspects. Okay, and that thinning can be significant to weaken the base metal itself. Okay, so so this is one aspect where due to the application of the pressure, thermal softening, and these special indentation marks being developed on the surface of the base metal, thinning of the base metal takes place. So these are, you can say, indentation marks being developed in the work pieces. So here if we see the different joints being developed using the different level of energy, 75 joule, 125 joule and 200 joule. What happens that a joint interface is not perfect. There is no bonding is imperfect when the amount of energy supplied is limited, and quite good joint is being developed, but there may be a minor unbonded regions here and there, and perfect joint is developed at the 200 joule. So this is what we get here in terms of the joint load carrying capacity. When the energy supplied is very limited, our bond strength in terms of the load carrying capacity is very low, and that is primarily attributed to the presence of unbonded zones here and there. Although thinning is very limited when the energy supplied is less, thermal softening would have been less, and there is no major indentation marks on the surface of the sheet metal being joined. Okay, but when we increase the amount of energy supplied, the interfacial bonding improves the joint strength. At the same time, deformed thickness of the base metal is also decreased. So you see this green line is indicating that deformed thickness, that is thickness of the parent metal, is getting decreased, but the joint strength is getting improved, and the bond density or the bonded zone is also getting increased. So this is very interesting thing. In one hand, the sheet metal thickness is getting decreased. On the other hand, the bond strength is getting increased. So if we just see we are having a very unique situation. In one hand, with the increasing weld energy, the sheet base metal sheet thickness, deformed sheet thickness is getting decreased. On the other hand, the bond area or the bond interface joining, which is being quantified as and similarly the joint strength is also increasing. But here if you see, there is some optimum value of the weld energy that we have to apply for the maximum joint strength, and thereafter we'll notice that the joint strength is getting decreased. So if we simply plot the energy as a function of the, let's say, the load carrying capacity, then it will be initially increasing because of the increasing the bonding between the base between the sheet metals, but after reaching to the peak value, further increase in the energy decreases the load carrying capacity, and this is attributed to the thinning of the base metal. Okay, reduction in the or deformed thickness of the base metal, which is being left due to the higher amount of the energy application. So significant reduction in the thickness of the base metal will be weakening the base metal sheets itself, and that is why your load carrying capacity of the ultrasonic weld joint is reduced. Here if we see, for a given setting, if we increase the weld time, that in turn will be increasing the welding energy also. So increasing the weld time is increasing the joint strength up to a limit. Thereafter joint strength starts decreasing, but the bond density or the interfacial bonding will keep on increasing certainly, but at the same time the post weld thickness percentage, you see, post weld thickness, when we use less step time, the thickness percentage is high, say 40%, but this thickness percentage is dropped very badly, means the thinning of the base metal has taken place significantly, and that is why we have to have an optimum level of the thinning as well as the interfacial bonding for maximum load carrying capacity of the joint.
Today we will be discussing about the ultrasonic welding of the plastics. So these are the main building blocks or the main components of the machine. Here is the compressor of the machine, which generally needs to generate a pressure inside them to carry out the welding process. So here is the main machine assembly. Here we can see this is the main part of the joining process. So this we call as a ultrasonic horn, and this is the main heart of the machine. So the ultrasonic vibration, for the ultrasonic vibration, this horn will produce the ultrasonic vibration during the welding processes. Here we can see there are two clamping arrangement is there for by which we can clamp the samples in this particular mold. Here we can see the control panel. So basically we have three parameters to control during the welding process. One is time, one is pressure, and third one is amplitude. So in time we have the weld time. In case of pressure we have welding pressure, and in case of amplitude we have amplitude. Third parameter is amplitude. Now suppose we want to join this plastic part. So these are the samples of HDP, high density polyethylene. So we generally need to keep it here like this. This is basically for the support of this second sample. So this second sample we will keep place here. As you can see, here is the marking shown in the mold. So this marking is 25.4. So it is according to the standard of the plastic joining. So we need to clamp then this and need to close the machine. These are the setup for the joining process to make a start. Here you can see the welding wood is taking place. We can remove the clamping, and here we can see the joining is taking place between the two samples. Okay, thank you.
Good morning friends. Today we are going to have a demonstration of the ultrasonic welding setup for plastics. So here we see that we have an ultrasonic welding machine, and the basic principle of ultrasonic welding is the ultrasonic vibrations. So we normally create heat at the interface of the two surfaces or the two adherents to be joined together, and then we apply pressure to join the two plastic parts together. So here we have a ultrasonic horn here inside the working chamber, and then we can place the two samples to be joined together like these. These are the two samples which are the plastic parts to be joined together, and here we have got the sample or the machine retrofitted as per the ASTM standard. So the joint overlap area or the joint area will be 1 inch by 1 inch. So I will try to show you the joint specimen of 1 inch by 1 inch area. So these are the two individual samples which are the plastic parts which have to be joined together using the principle of ultrasonic welding. So the theory has already been discussed with you in the theoretical classes, as well as the PowerPoint presentations are available with you. This is the setup that we use for making the ultrasonic welded joint. So this setup is dedicated for plastic parts, the ones that we can see here. So what we do here, we place the two samples in the lap joint configuration. So our setup is going to join the two samples in the lap joint configuration. So we fix the two samples here, and then we fix them in the lap joint configuration, and then we close the gate like this. So there are safety features which are pre-integrated into the machine. So we close the gate before we start the machine. So the parameters can be controlled from this control unit. So we have a control unit here through which we can control the operating parameters. So we control the parameters, and then we can see that the joint is formed. So it is a very fast process. We can form the joints within few seconds, sometimes maybe within a second also. So this is a fast process. Very soon the heat is created at the interface because of the vibrations, and therefore we are able to produce the heat by the pressure that is applied on the top. So maybe in the meantime we can see the samples have been fabricated. This is the sample, you can see there is some flash on the side which has been joined. Now even if we apply the load, it will not fail. So even on the application of load, we see that it is a very good joint which has been formed. But now if you see, there is flash on the side of the joint. This flash we have to see that how we can remove this by optimizing the parameters. There are number of parameters which can be optimized here. So we can optimize the set of parameters that we see here, because here the flash is more, so we can control the time, we can control the pressure, we can control the amplitude. So we can control different parameters and try to find out the optimal combination of time, pressure and amplitude to form a good quality joint. So this is the good quality joint that we see here. So when we get the right combination of time, the time for which we are doing the welding process, we control the pressure and the amplitude. When we control all these three parameters in the optimal manner, or we find out the right combination of these three parameters, the time, pressure and amplitude, we get a very good quality joint like this. So this is the good quality joint that we see here. This is a poor quality joint that we see here, because there is a lot of flash. So we can optimize the three set of parameters from the proper selection from the control panel, and we can get very good quality joints like this. So this is the ultrasonic welding process for plastics. Thank you.
Ultrasonic welding. Ultrasonic welding is a solid-state welding process. This process does not involve the use of electrode or filler metal or generation of arc. It is a welding process which uses ultrasonic vibrations to weld or join. Working principle of ultrasonic welding. The weld is produced by the application of a high-frequency ultrasonic vibrational energy in the order of 20 kHz to 40 kHz. This causes friction and hence heat is produced at the point of contact between two workpieces to be joined together, thus producing a metallurgical weld or bond without melting the metal. Parts of ultrasonic welding machine. Power supply. A normal line voltage of 240 V is applied. Transducer or converter. A converter is used to convert the high-frequency electric signal into high-frequency mechanical vibration, and it does so by using the piezoelectric effect. Booster and horn. A booster amplifies the frequency and is then supplied to the horn. Horn transmits this vibrational energy to the workpiece. Fixtures. Fixtures are the devices used to hold and clamp the two workpieces together. Working. The parts to be joined together are held in contact with each other under pressure by using the press and fixtures. Then high-frequency electric signals are then converted into high-frequency mechanical vibration with the help of a converter or transducer. Then it is fed to the booster, which amplifies the vibrational energy. This high-frequency vibrational energy is then transferred to the workpiece to be joined together with the help of a horn. This vibrational energy at the contact between the two workpieces generates local friction and shear force and produces plastic deformation, thus generating heat, and the two pieces are joined together at the interface metallurgically upon cooling. Advantages. Since no heat is supplied and no melting occurred, therefore heat affected zone is minimum. Very thin materials can be welded. No need for electrode and filler material. Dissimilar materials can be welded. The process can be automated. Provides good surface finish after welding. Disadvantages. This welding process is limited to thin malleable metals and for small welding areas. It is limited to lap joint. Due to fatigue loading, the life of the equipment is short. Tooling cost and fixture is high. Application. It is used in electrical industry to produce delicate circuits, flash drives, and semiconductor devices. Aerospace and automotive industries to produce door panels, steering wheels, and other engine components. In the medical industry to produce parts like filters. If you like this.
So considering the various aspects related with the kind of thinning which is taking place, or the kind of interfacial bonding taking place, or the soundness of the joint or the kind of metallurgical transformations which are occurring at the ultrasonic joint interfaces, or the load carrying capacity of ultrasonic weld joint needs to be analyzed. So we can conclude here we have seen the kind of procedure which is used and precautions to be used for developing the ultrasonic welding. Investigate the effect of the various welding parameters like the pressure, the welding time, or the energy being applied. Observe the way by which the joint interface characteristics or the microstructural aspects and mechanical properties of the joint are being affected by the various welding parameters.